So spherical coordinates are a completely different animal, and that's why we're going to spend most of the time in this section on spherical coordinates. I have this pole, which is my z-axis for reference. I think it'll be easier with a visual. Okay, so what's happening with spherical coordinates? And like maybe let's say here's the origin. So there's going to be the Greek letter rho is going to be like your r from before. But instead of just being in the xy plane, so like in cylindrical coordinates, it worked out that little r was your distance from the z-axis. Now rho is going to be distance from the origin. So instead of cylinders, we're back to spheres. Okay, so like rho equals 5 is the equation for a sphere of radius 5 in cylindrical coordinates. This isn't really helping yet. It'll help when we get to phi. Okay, theta is going to be the same thing that it was in polar coordinates. So if you look in the xy plane, your theta is the angle with the positive x-axis. And same thing as you go up to higher planes, always think of theta as the angle in that horizontal plane with what would be corresponding to the positive x-axis. So that's good. Theta is the same. And then the new thing is an angle phi. And I'll write down all these symbols when we get to the second half of the video. Phi is going to be the angle measured with the positive z-axis, but it works fundamentally differently from theta. Theta is always looking in a horizontal plane and measure the angle. Phi is just measure the angle in three-dimensional space with the positive z-axis. So how does that work? Well, if we're on the z-axis, then the angle with the positive z-axis is 0, if we're on the positive z-axis. As we come away from the z-axis, then you're going to draw a line basically to the origin and look in 3 dimensions at that angle. Okay, so if I wrote an equation like phi equals pi over 6, 30 degrees, then I'm looking for everything, like everything on this line works. Let's say that's 30 degrees, right? But I can also rotate this line. As long as I maintain this 30-degree angle, I can rotate it anywhere. It always makes a 30-degree angle with the positive z-axis. And so like what shape do I get when I rotate that? Well, I'm actually tracing out half of a cone. It's maybe what we think of as a cone, but in math there's cone is actually a double infinite cone, really weird. So in math it's half of a cone. Okay, so the equation phi equals pi over 6 is going to be half of a cone. And that's really cool. When we start doing problems, you'll see that spherical coordinates are really good for working with problems that have both a cone and a sphere in the problem. And the integration will be a lot easier that way. All right, so now that we've introduced a bunch of weird variables, we have to figure out what all the conversions are. So first, let's maybe think about what z and x and y are equal to. And in order to do that, we need a picture. So here's our x, y, and z axis. Okay, and let's see. So z, if I have some point here, and like this angle is phi, so phi, here I'll write phi twice. So it's spelled this way, first of all, phi. I think a lot of students aren't familiar with the Greek alphabet, so I'm going a little slowly with this. And then when it's typed, you'll see it like this, but sometimes when it's handwritten, we write it like that, and you're welcome to write it like that. It's a little bit faster to write, maybe a little bit more fun. So that's phi, and then rho is like what a radius is going to be now. That's a Greek letter that looks like that. It looks the same handwritten and typed. And then, of course, theta is the same as before. We also have theta. Theta. Okay, so those are the 3 Greek letters in spherical coordinates. Okay, so if I have some point in 3 space, then that length to the origin is rho. The angle, looking in 3 dimensions at that angle, is phi. So if I wanted to find the z-coordinate, I would drop a perpendicular to the z-axis, and then I just have to do some trigonometry. So z is going to be rho cosine phi. Okay. A little bit harder to find x and y because now I have to drop a perpendicular down to the xy plane, right? And now, let's see. Those are parallel. So let's put the y-axis back. That length was rho. If that angle there was phi, then this angle over here was phi. It's like alternate interior angles or something from geometry. So then this length in the xy plane is rho sine phi, right? And so then to find x and y, I drop another perpendicular from that point in the xy plane to the x-axis. And now I can find my x and y. We said theta was the same, so that angle is still theta. So then my x component there is then rho sine phi, which was the hypotenuse, times cosine theta. And then the y component is hypotenuse of the triangle, rho sine phi, times sine of theta. Okay, so that's how we convert from rectangular to spherical coordinates. Going backwards is a little tough. So you can check this algebraically too, but since rho is distance to the origin, then x squared plus y squared plus z squared is rho squared. You also have this conversion, x squared plus y squared is rho squared sine squared phi. You can check that algebraically using those two equations. Okay, so in order to find phi, if we wanted to, then we would probably say something like tan squared phi is x squared plus y squared over z squared, so that's actually kind of tough. The easier one is theta. Tan theta is still y over x, so that's good. Okay, so we can pretty much convert backwards and forwards. On the second part, we might have to be thinking about some domain things, like especially with that equation, positive or negative. Might be some funny business. You just have to look at it. Luckily, phi only goes from, only needs to go from 0 to pi, right? Because angle with the positive z-axis is 0 there, and then going, we already end up down here when we get to pi. We don't need to go around because every single angle is tracing out a cone all the way around, so we're good. Okay, then next thing we need to do is we need to think about like what does dx, dy, dz convert to in spherical coordinates. And then remember how we did it with polar. Dx, dy was r dr d theta. And why was that? It's because when you looked at your polar graphing paper, where you had radial lines and then you had circles, your little regions out here were a lot bigger than your regions down here. And the reason for that was your dr was the same, but your d theta was a lot bigger. Your d theta was actually, or your change in the theta direction was actually r d theta. Okay, so same phenomenon is happening here, except we're in more dimensions. So we're looking at spherical shells. So d rho should probably be the same. And then they change in the phi direction and also in the theta direction. Your r d theta, well, r, we said, r is like what we got down here when we projected onto the xy plane. So r is like rho sine phi. So theta direction. So in our theta direction, we wanted an r d theta, and what we're really going to get is rho sine phi d theta. Okay, so we can go ahead and multiply that on. D rho times rho sine phi d theta. And then what about in our phi direction? So that's three-dimensionally, how is that changing? Well, phi actually acts like theta used to now. So the way it changes, let's see, we're really doing conical shells, so it's kind of hard to visualize. But you can see that the same thing will happen, right? If you take spheres, the farther out you go, the bigger that change is going to be, even though the d phi is still the same. So maybe I can convince you that way that in the phi direction, we're changing by rho d phi. Okay, so what we end up getting is dx dy dz gets replaced with rho squared sine phi d rho d phi d theta. That's just what gets replaced. So if you're integrating a bunch of stuff, you have ugly function, and then you need to multiply that function by all of this at the end. These are going to be extra factors that show up every single time. So d rho, d phi, d theta. Okay, so we'll see lots of examples of that because the integration actually gets a little bit funny sometimes with that.